Welcome back to Transforming Rational Functions into Infinite Series. This is part 2, and we'll be looking at proper rational functions with a denominator of degree 2. So first, we saw that any proper rational function with a denominator of degree 1 can be written as an infinite series with coefficients that are part of a geometric sequence. Now we have a rational expression with a numerator a plus bz, where b of course can be 0, and a quadratic denominator alpha plus beta z plus gamma z squared. Like last time, Euler says, let's set this equal to an infinite series a plus bz plus cz squared plus dz cubed, etc. Then once again, he cross multiplies to get a plus bz equals alpha plus beta z plus gamma z squared times a plus bz plus cz squared, etc., which he multiplies out to alpha a plus alpha bz plus alpha cz squared, and so on, plus beta az plus beta bz squared plus beta cz cubed, and so on, plus gamma az squared plus gamma bz cubed plus gamma cz to the fourth, and so on. Then he groups the terms to get coefficients of the powers of z. And remember, a plus bz equals a plus bz plus 0z squared plus 0z cubed, and so on. So he matches the coefficients of both sides of the equation. So then he gets little a equals alpha times big A. So big A equals little a over alpha. Now we say that little b equals alpha big A plus beta big A, and therefore big B equals little b minus beta big A over alpha, which equals little b over alpha minus beta little a over alpha squared. For the coefficient c, we set alpha c plus beta b plus gamma a equal to 0. And with a little algebra, we see that c equals minus beta b minus gamma a all over alpha. And c equals minus beta little b over alpha squared plus beta squared little a over alpha cubed minus gamma little a over alpha. In general, for any arbitrary coefficient r, we see that alpha r plus beta q plus gamma p, the two coefficients before it, is equal to 0. So therefore, when you solve for r, you get r equals minus beta q minus gamma p all over alpha. As we saw with coefficient c, its value begins to get messy as there's a new term in each of these coefficients, so it doesn't work out as nicely to write as the degree 1 rational function as an infinite series. However, what we see in front of us is a very special property that can allow us to more easily transform these rational functions into infinite series. Each coefficient depends on alpha, beta, gamma, and the two previous coefficients. Wait a minute. Doesn't that sound familiar? A number in a sequence depending on the two before it? The very famous Fibonacci sequence has that very property. The Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. If you've never seen this before, you might want to pause the video to figure out the pattern. But with that, I will skip to the answer. Each term is exactly the sum of the two previous terms. 5 is 2 plus 3, 8 is 3 plus 5, 13 is 5 plus 8, and so on. Knowing this, it's now possible for us to come up with a rational function with a denominator of degree 2 that transforms into an infinite series with the Fibonacci numbers as its coefficients. To do this, we would want both beta and gamma to be -1 and alpha to be just +1. Or we could have beta and gamma as positive 1 and alpha as negative 1. It doesn't really matter. But let's use beta and gamma equal negative 1 and alpha equals 1. And of course, we would have to set up a and b to equal 1, as they don't share the property of depending on the previous two coefficients, as they are the first two coefficients. Since alpha is 1, little a needs to be 1 for big A to be 1. Minus beta big A equals 1, and alpha equals 1, so little b needs to be equal to 0. So now we have little a equals 1, little b equals 0, alpha equals 1, beta is negative 1, and gamma is negative 1. This gives us the rational expression 1 over 1 minus z squared. We can confirm this gives us the Fibonacci numbers as coefficients by performing the original transformation. So 1 over 1 minus z squared is equal to a plus bz plus cz squared, blah, blah, blah. And that means that 1 equals 1 minus z squared times a plus b plus cz squared, etc. And when we cross multiply, and multiply it out, we get 1 equals a plus b minus a times z plus c minus b minus a times z squared plus d minus c minus b times z cubed plus e minus d minus c times z to the fourth, and so on. What we'll have is a equals 1, and then b minus a equals 0, so b is a, which is 1, and then setting all of these new coefficients equal to 0, you can clearly see that each of their original coefficients is equal to the sum of the last two. Therefore, we have that 1 over 1 minus z squared equals 1 plus 1z plus 2z squared plus 3z cubed plus 5z to the fourth plus 8z to the fifth, and so on, with each coefficient being the nth Fibonacci number. Okay, part 3 we'll look at bigger degree rational functions. Get lost.